Hello everyone. Today we're going to look at two other equations in electrostatic. One is the voltage problem and the other one is electric potential energy problem. Now let's first examine potential energy. Just like any force, when you have a force like gravity, there must be a gravitational potential energy, which is the amount of energy that you need to actually work against or with the gravitational force. So electric force can also provide some kind of attraction or repulsion. So therefore, if you want to work against that force or with that force, there will be some energy that you need to supply, or there are some energy that you can actually get out from it. Now, potential energy could be used to attract. So you can have potential energy that's attracting or repelling. So attract or repel, depending on the charge. So depends on the charge. Potential energy could be either attracting or repelling. So in a non-uniform electric field, which is that the one that's provided by a single charge, like the one I have in here, like a proton or electron, we call it a non-uniform field because the electric field actually gets weaker as you go further away. So it's not the same no matter how far you are. We call that non-uniform. There is a way to make something that is uniform called uniform electric field, but that will be a topic for later. Okay, so now let's see. Remember, now how do you get energy? Remember, energy or work done could be force multiplied by distance, right? Now in this case, the force is electric force. So instead of like an applied force, we are saying that it's electrostatic force that's pushing the object. So the work done would be electrostatic force. So the work done in an electric field will be a electrostatic force multiplied by the distance that it moves. That can be stored as some kind of potential energy, right? So that's a kind of potential energy. So the work done can be stored as a potential energy. So for example, if you put a proton next to a proton, they're both positive. Before you release the proton, they have potential energy. And they gain kinetic energy, very much like gravity. You can store energy. You can store energy also in electrostatic force. Now, the equation for electrostatic force is something that we learn is the Coulomb's law, which is the equation that is K Q1 Q2 over R squared. That's a Coulomb's law, right? And now we have to multiply that by the distance. In this situation, the distance and the D and the R is actually the same thing. It's just that we use different symbol in different equation. So therefore, you can actually cancel it out. And now, as I know, change in potential energy is Q1, Q2 over R. So it's very similar to the equation of the force, which is K Q1 Q2 over R squared. The only difference is there is no square in this one. Now, if you've been following the lessons, for the first class, we have the Coulomb's law for forces, and the second class, we have the electric field. Both cases, we put absolute value in the equation. Now, in this situation, though, however, we don't. This potential energy can actually be positive or negative. It actually does make sense for it to be positive or negative. So we are keeping the positive and negative charge. Okay, so we're actually keeping the sign on the charges. So very unlike the first two equations that we learned in week 1 and week 2, where when we have those charges put in this situation for potential energy, we keep all the charge. So when we keep all the sign. So when the potential energy is positive, that means we are working against the force. So you need to input positive energy into the system if you try to work against it. So for example, what is working against it? If you have a positive charge and you want to push another positive charge close to it, for example, like this action, if I'm trying to push this second positive charge close to the first one, okay, then I will need positive potential energy. Now, however, I don't need to do anything. I will just let them go and then they will separate by themselves if I have two protons close together. So the potential energy will be, change in potential energy will be negative if you're working with the force. Okay, so now that we have this equation, let's one example. How much energy work must be done to bring a 4 microcoulomb charge object to within 1 meter of a 6 microcoulomb charge object from a long, long away? So from far, far away. So at the beginning, okay, so at the beginning, you have this 6 microcoulomb charged object, which is charge 1, and you have this 4 microcoulomb charge object, which is a little bit further away. Okay, so this is your initial picture. Okay, this is your initial picture. So what are you trying to do? So this is picture, this is before. Okay, so that's your before picture. So what you're trying to do is you want to bring the 4 microcoulomb one. Okay, so you want to bring the 4 microcoulomb, which is the smaller one, close to this first one. Okay, so you want to bring that close to it. So you want to do this, basically. Okay, now, okay, so how close do you want to bring them to? You want to bring them close enough so that they're only 1 meters away from each other. Okay, so how much energy? Now, why do you need to actually put in some work in order to do that? It's because these two charges are both positive, so they inherently want to stay away, and you're forcing them to go together. So in this after picture, you want to force them to stay together, so you need to input energy because they don't really want to be together. Okay, all right. Okay, so what's your change in potential energy? First of all, what is the initial potential energy? Well, the initial potential energy is going to be kq1 q2 over r squared over r. But what is the distance between the two objects? They said really, really long away. Now, really, really long away in physics means we can say infinity then, right? So imagine what that equation actually gives you if you have the really, really long away. So it's k q1 q2. So it's like k q1 q2 over r. But the r is very, very far away. So what happens when you take something and you divide by infinity? You get close to 0, right? You get close to 0. So we always assume that your potential energy at really, really far away is 0. Okay, your potential energy after. So this is your potential energy after, so final. Now that we can use the actual equation to get k q1 q2, and this time is over 1 meter because it's over r squared, right? So over r, sorry, I'm saying over r squared because that's the potential energy, that's the force equation. Now k, which is 9 times 10 to the 9, so I'm not going to write that. q1, which is 4 microcoulomb, 4 times 10 to the negative 6, and q2, which is 6 microcoulomb, 6 times 10 to the negative 6, and over 1. So you don't actually have to do over 1, so just. Now, at the end, the energy, 0.216 joules. Okay, so work done is always change in something, change in potential energy. And in this case, the change in potential energy, which is final minus initial turns out to be exactly 0, so we are good. We are good to go then. So the energy level is 0.216 joules, and that's it. Right, because the final is 0. The initial is 0, so we don't have to actually count that. All right, so that example is done. Now remember, potential energy is a scalar. That means you don't have to worry about left, right, up, down, east, west. You don't have to worry about direction, but you do have to use plus or minus sign. Remember, the best analogy is money. Money does not have direction, but money can have positive and negative sign depending on if you have money or you're borrowing money or you're spending money from your account or you are depositing money to your account. So we will use plus or minus signs. So if that question that we just did was for electrons, so or one of the charges is electron, we will use negative sign. Okay, so keep the sign. Actually use the plus or minus sign. So don't do the absolute value thing like the first two equation, the force and the electric field. For potential energy equation, you keep the sign for the charges. Okay, so if it's a positive charge, you use positive charge. If it's a negative charge, then you use a negative charge. Okay, so now, so in this case, just a summary, bring a positive charge near another positive charge requires input of energy. So you actually have to put energy in order to do that. Therefore, the work done is positive. Okay, so you're working against the force. So therefore, the work done should be a positive number. So now let's look at another situation then. How much work is done when a negative 7 microcoulomb charge is brought to within 0.5 meters of a 5 microcoulomb charge object from a long, long way. Again, remember, so I don't think we have to worry about this. From a long, long way means initial potential energy must be 0 because you're so far away, right? So that's the same argument that we make with the last equation. So now we say, okay, so let's put the 5 microcoulomb charge here, and let's put the negative 7 microcoulomb negative charge over there. So negative 7. So negative 7 microcoulomb charge over here. So initially they're really far away. And then what happened is you are going to bring that very close. So you're going to bring that until it goes into maybe, okay, so until it goes like over here. Okay, so how close is that? Now this is going to be the final distance between them is 0.5 of a meter. Okay, so 0.5 of a meter, 0.5 meter. All right, so it's going to be very similar to what we just did, except that we keep the sign. So it will be a negative. So the work done is your change in potential energy, which is final potential energy minus initial potential energy. But in this case, the initial potential energy is 0 because they are really far away. So the final potential energy is your work done. So your final potential energy is K, Q1, Q2 over R, which will be K. So Q1 is 5 microcoulomb. Q2 is negative 7 microcoulomb. And for the first time, we are actually using negative sign in our calculation, and then over R, which is 0.5 of a meter. Now, you have a calculator, put that in, and you get this negative 0.63 joules, which makes sense because you don't actually have to input energy to do this. The negative charge, this negative 7 microcoulomb negative charge, wants to get close to the positive. You just have to let it go, and then it will go on its own. So you don't need any positive energy to make this work. This should work on its own. So when you're bringing a negative charge near a positive charge, or vice versa, you are releasing energy. Just like, from gravity, right? When you drop something, you're releasing energy. Therefore, the work done is negative. You don't have to actually do any work to make this happen. Okay, so that's half of it.